Okay, next point of interest we are going to talk about is called the fat tail distributions, and these are the kind of distributions which have fat tails or heavy tails in other way. And they are characterized formally in several ways. For a non-negative distribution, one general description is to state that fat tail distribution is one whose tail is not exponentially bounded. So what we have, what we may say here, we may also say that the distribution fx, where x is a non-negative random variable, is fat-tailed if the moment generating function is in the form of e to the power of tx. Okay, and let's place this function over here. First, fat-tailed. So moment generating function is always mxt, and mxt is just the expected value of exponent to the power of tx. Okay, so we have this moment generating function, and the only parameter here is actually t, and t is just the positive value. T is more than 0. The literature on fat tails is extensive, and we can discuss for different kind of distributions, but we generally have to define something like the characteristic of the shape of the probability density function. So what am I talking about? Let's look at this picture, and let's look at this picture of normal distributed numbers like that. So what can we say about the probability density function of the normal distribution? What can we say about the shape of the normal distribution and the kurtosis? The kurtosis actually is a measure of the peakedness of a density. Okay, so the normal distribution function is have the PDF, the probability density, which looks like the bell shape. Okay, this is the bell-shaped curve. So the peakedness of this function is like this, and this picture, as you remember, is just the generation of the 1 million random distributed normal values. So the peakedness here, we can measure the peakedness of different distribution in comparison to the normal distribution. And the coefficient of kurtosis is defined for distributions with finite fourth moment. So fourth moment, as you can understand, this is kurtosiness, and it is based on this fourth central moment. So in terms of normal distribution, this coefficient of kurtosis is free. It equals to free. So the distributions with a coefficient greater than 3 are said to be leptokurtic. So we can generate this term like that, leptokurtic distribution, if the kurtosis fourth moment is larger than 3. Normal distribution has kurtosis of 3 equals to 3. Okay, so we just have to compare the value of kurtosis. Is it equal to 3? Then we are talking about something which looks like the bell-shaped curve. And if we don't have that, if we have the kurtosis larger than 3, that means we are talking about leptokurtic distribution. And greater than 3, that means it has a more sharply peaked density function. So instead of this smooth density curve, we'll have something which is maybe a little bit narrower than that, and the peak will be higher, and it will be sharper in its visualization. Okay. Different thing which we might compare to normal distribution, which has this leptokurtic shape, is the student's T distribution. The student's T distribution. Okay, students. You might have encountered this distribution in your course of statistics, where you tested the value, see if the sample mean is this particular value or not, or if you can compare this sample to that sample in terms of their mean or median value. So in these tests we use the student's T value just to compare the sample means. Or we might use the student's T distribution to find out the quantiles which are used to understand whether the coefficient of the regression function is significant or not significant. So the student's T value has slightly higher, slightly fatter tails than the normal distribution. Okay. So while the coefficient of kurtosis can be calculated for skewed distribution with fourth moments, its interpretation is straightforward for symmetrical peak distributions, so we always compare to normal. Its numerical value for skewed distribution, while it can be interesting, is not particularly useful. And the coefficient of kurtosis generally it is scale free. That means if kx value has the same kurtosis as x value. So for example, kurtosis of gamma of alpha lambda does not depend on the scale parameter. The 2 parameter gamma alpha lambda has the same kurtosis as the 1 parameter. So let me summarize that in the writing form. The kurtosis of gamma, let's say like that, gamma alpha lambda this parameter does not depend on the scale parameter, on this alpha. It does not depend. So we have the here a 2 parameter distribution with alpha and lambda. Okay, so this first letter is the gamma. It is a Greek letter gamma. Okay, so the 2 parameter kurtosis has this this distribution has the same kurtosis, which does not depend on the alpha parameter, and the kurtosis will be the same if we just forget about the second parameter and consider only the distribution with 1 parameter. Okay, like that. It has the same thing as with gamma alpha 1. In the case that x has a finite moment generating function in the neighborhood of the origin, central moments of order 2, 3, and 4 can be found from cumulant generating function. Okay, and the cumulant generating function, the maybe not very useful for you to practice, but still we have to place this formula. Kxt is the log mxt. So this is our cumulant generating function.